the movie The Matrix came out when I was in high school, which I realize that I'm not like really old, but it's been long enough. So raise your hand if you remember discussing matrices last year in class.
I remember.
Okay.
Don't say that too quick. Yeah, I got a feeling it's going to be a little bit difficult.
So we are going to build off of what you did in Algebra 2. Really, if you looked at matrices, you looked at them for like 3 days. You added them together and you multiplied them together. Okay? We are going to do that on Friday. But there's a few things that we need to talk about with our matrices that we can do since we just came off of our solving systems chapter. Okay? So first of all, a matrix is a rectangular array of numbers. Kind of like a table, right? Table of numbers. We have rows, we have columns, and then we have these like bracket things on the outside. Okay, those brackets scream, hey, I'm a matrix. Those of you who have taken the ACT, have you seen a matrix on the ACT? Yep. Yep, you have. Okay. Each number in the matrix is called an entry. Okay, something that's very important, especially when we get to Friday when we're adding and multiplying matrices, is what we call the order. Okay, the order of the matrix describes how many rows and columns that a matrix has. So tell me, how many rows does this matrix have?
3.
How many columns?
2.
Okay, so we call this a 3 by 2 matrix because we describe the order by the number of rows by the number of columns. Okay, kind of like a piece of wood, right? Like a 2 by 4. Okay, this is how you would write it. Okay, so on the next slide there are 4 matrices. I'm going to give you a minute to work with your table to identify the order of each of them. Okay? Dallas, what's the order of A?
1 by 1.
There is 1 row and 1 column. Callie, what's the order of B?
1 by 4.
There is 1 row and 4 columns. The order of C. Emma Stuck.
2 by 2.
There are 2 rows and 2 columns. We actually would call this like a 0 matrix. Why would I call it a 0 matrix?
0.
They're all zeros. Okay. And then D. Kaylin, what is that?
3 by 2.
There are 3 rows and 2 columns. Okay? It is important that you can identify the order because come Friday, we're going to have to pay very close attention to the order and order to be able to do our operations. Okay? So I know that you've worked with matrices before, but you've never worked with them in the manner that we're going to today. Okay? So a lot of today is unfortunately going to have to be getting used to some new vocabulary. Okay? The first thing that we're going to talk about is an augmented matrix. And an augmented matrix is a matrix derived from a system of linear equations. Did we just do a bunch of work in solving that? We did, right? Yeah. Okay. So take a moment and write down the definition with this system of equations, and then I will show you what an augmented matrix is from this particular system. I would, so then when we write the matrix, it makes sense of how you got all the numbers. Okay. So yes, I would write down the system. We're not going to solve it until tomorrow. Who can tell me the order of the matrix we're about to write down? If I throw all of these numbers in a matrix, Max, what's it going to be? It is going to be a 3 by 4. We're going to have 3 rows and we're going to have 4 columns. Okay? Essentially what's going to happen is each row is going to be an equation and each column is going to be a different variable for the constants. So our first row would be 1, -4, 3, 5. And there's actually like some dots in between to separate kind of like where the equal sign is. All right? And then our second row would be -1, 3, -1, -3. Essentially, I'm taking the coefficients and throwing them in there. Okay? Now, to be consistent, our last row, what would it need to be? 2, 0, -4, 6. Okay? We call this augmented because we basically have all of the coefficients and then we extend it out by a column for the constants. Okay, so that's why it's called augmented. Okay, and we have these dots here. This is the only time you're ever going to see something other than numbers inside your matrix is basically these dots. Sometimes people will draw a line, but our book uses dots to separate constants from the coefficients. Okay? So what I'd like you to do is I'd like you to take some time at your pod and put this one into an augmented matrix for me, please. Getting emails. Compare it to your neighbor. Braden, what's the order of the matrix that you wrote?
I put 1.
Well, what's just the order?
Oh, the order?
Mm-hmm.
Like 3 by 4.
Okay, we have a 3 by 4 matrix because we have 3 rows, 4 columns. Do you think that in a 3 variable system that's going to be pretty typical? 3 rows and 4 columns, right? Okay. So Sydney, can you read your first row to me?
I have 1, -2, 3, and then dots, and then 9.
Okay. Good. Our second row. Adding up.
-1, 3, 0, and then 4.
Zero's in the right place? Because it's representing Z. There's not a Z, so we put a 0 there. Okay. Jessica, last row.
2, -5, 5, 17.
Excellent. Okay. All right. Well, why are we going to do that? Okay. Eventually, everything will piece together, but we are going to talk about what we can do with rows. So we have what's called elementary row operations, where we can do 3 different things with our rows. And essentially, they are things that we could do with the actual equations themselves. But having them in a matrix, we don't have to worry about the X's, Y's, and Z's. And we can keep them all organized inside of that one matrix. Okay? So the first operation we can perform would be to interchange 2 rows. Okay, so I'm going to get real crazy here with my matrix. 1, 2, 3, 4, 5, 6. Okay, and we can interchange 2 rows. So I can take 2 rows and I can just flip them. Okay, and I want you to notate what you're doing. So if I'm going to exchange 2 rows, then I'm saying, all right, I'm taking row 1 and I'm switching it with row 2. So then my new matrix would be 4, 5, 6, and 1, 2, 3. Okay. You think about a system of equations. It doesn't matter which equation comes first, which equation comes second. It is okay to switch your rows, okay, when that's what they're representing. Okay. What else can we do with an equation? Can we take an equation and multiply by a number on both sides? Right? If I have an equation, can I multiply both sides by a constant? Preferably not 0, because then it's kind of a waste of your time. So you can multiply a row by a non-zero constant. If a row is representing an entire equation, multiplying a constant through is essentially the same as multiplying a constant to both sides of your equation, which is legal. If we do it to one side, we can do it to the other. So, for example, with my 1, 2, 3, 4, 5, 6 matrix, we could take row 1 and multiply it by -4. And if we do that, we would get -4, -8, -12, 4, 5, 6. What? Yes, if you are multiplying, you have to multiply the entire row, but you just do one row. Okay? You're multiplying the row. Okay? And our last operation is that we can add a multiple of a row to another row. So essentially we can add rows together, okay, whether it be a multiple or not. Okay. when you do the process of elimination in a system of equations, right, what do? You multiply an equation and you add them together, right? Okay, that's essentially what this is doing. So we have 1, 2, 3, 4, 5, 6. What we could do is we could take row 1 times -4 and add it to row 2. Okay, so if we do that, we could keep row 1 the same, but we can still multiply it by -4 and add it to row 2. So we'd have -4 plus 4. We'd have -8 plus 5. And we'd have -12 plus 6. Any questions on that?
So you wouldn't write the top row multiplied by -4?
Nope, you can leave it the same. Okay, you can leave it the same. And I'll talk about why leaving it the same will be beneficial once we have another vocabulary term. Okay. So your book is going to ask you to do some row operations for you to get the practice. Okay. So I am going to have you write down this matrix. And do you notice how I notated what I was doing? Like with the R1 and R2. Okay, I am going to ask you to do that whenever we perform an operation. Okay. So for example here, I'm going to ask you to switch rows 2 and 3. When you do that, notation-wise, I want you to tell me that you're switching row 2 and 3, and then write the matrix where that actually occurs. Okay, and rows are, they're stuck together, okay? So here would be switching row 2 and row 3, okay? Now from this matrix, I would like you to take row 1 and add it to row 3. Is that legal to add rows together? Okay, but I can only replace one of the rows. So what I'm going to write is I want you to take row 1 plus row 3 and replace the old row 3 with what you get. Okay, so what this means is row 1 and row 2 get to stay the same. But now, look at the matrix from before, add row 1 and row 3 together, and that's your new row 3. Add row 1 and row 3 together. So what do we get? 0, -1, 2, 2, right? We add those rows together. All right. Okay. We have some writing to do on the next page. All right. There's going to be some descriptions about what's called row echelon form, and we're going to need to write them down. And I know that's not like fun and exciting, but I need you to know what it is. Okay. We're going to do a lot more work with it tomorrow, but I need you to understand what it is. So first of all, write down row echelon form. Row echelon form. If we have an augmented matrix and it's in row echelon form, this is what it would look like. If there is a row of all zeros, it has to go to the bottom. You're not going to see that very often, but if it happens, it happens. All other rows have the first non-zero entry as 1. So it could be 0, 1, blah, 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 blah. It could be 0, 0, 0, 0, 1, blah, 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 blah. But every non-zero, the first non-zero entry is going to be 1. So it can start with zeros, but then the next number better be 1. It is okay if that doesn't make sense right this minute. I will give you a visual after we get our third stipulation written down. And this is the biggest, okay? For 2 successive non-zero rows, the leading one in the higher row is farther to the left than the lower row. Just write it down, and then I'm going to give you a picture, or a matrix. Here's an example of a matrix in row echelon form. Okay, so this right here, this really long one, for 2 successive non-zero rows. The leading one in the higher row is farther to the left in the lower row. Essentially what happens is we create like this diagonal of 1s. Because each row, as we move from bottom to top, the 1 is further to the left each time. You see that? Okay. Our rows begin with zeros until we have a 1. Or it starts with 1. Okay. Only one row can start with 1. The next row 0, 1. The next row 0, 0, 1. We had another row 0, 0, 0, 1. Okay. Does that make sense? Like that diagonal of 1s that I'm talking about? Okay. Now, tomorrow when we work with our calculators, we're going to talk about reduced row echelon form, where all you see are zeros and 1s and then some other numbers on the very, very right. So wherever there's a 1, there's a 0 above it or below it. Why would that be nice to have? If we had, if we did row operations and we got our augmented matrix to be in this reduced row echelon form, why is that nice? Oh, doesn't this mean z equals 7? And doesn't this mean y equals 3? And doesn't this mean x equals 5? Right? Isn't that nice? Okay. So while I'm thinking of it, I'm going to show you how to get a matrix into this form using your calculator tomorrow. So make sure you have it, so I can show you how to do matrices on your calculator. Okay? Now for today and tomorrow, we're really focused on how matrices can be helpful solving a system of equations. Okay? So I'm going to give you a row echelon form system real quick and talk about, yes, reduced row echelon form is nice because bam, 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 we know X, Y, and Z. But row echelon form is still nice. Let's talk about why. And we're probably going to be able to see your test today. I'm not excited though. Okay, so tell me one thing that we know right off the bat. We know that z equals -2. Okay. Okay, so we know what the very bottom is giving us something nice. Let's move to the next row. That next row, what does it mean? Y minus z equals 2. Well, if z is -2, do we know what y is? 0. And if you need to plug it in over here, like y minus -2 equals 2. Okay, y equals 0. Okay? And then our top row means x minus y plus 2z equals 4. Well, we know that z is -2 and y is 0. So that gives us x is 8. Bam! If we can get a matrix into row echelon form at the very least, it does not take us a lot of effort to figure out what x, y, and z are. And that's going to be what we work on tomorrow. Okay? I'm going to show you how to do this both by hand and with your calculator. Okay? Some of you are thinking, Mrs. Holman, why would you give us a different way to solve systems of equations? Is it nice to sometimes have choices how to solve a system of equations? I think it is. And all of you are in the moment of your life where you're taking the ACT, right? Okay, some of you seniors may be done, or you may be taking it in December. But those of you who are taking the ACT, I guarantee you there's going to be a system of equations on there. You have choices now of how you can solve them, and I'll show you how to do it tomorrow. But sometimes it's just nice, okay, to have options. Okay, so let me go